So the remainder of this unit will be focused on computing and performing hypothesis tests, assuming you've already gone over chapter 13. So for 9b, we're going to focus on the one sample hypothesis tests, and for chapter 10, we're going to focus on the two sample hypothesis tests. So here, the computation of our test statistic is going to be very similar to how we computed z-scores back in Unit 2. We're going to take the sample mean and we'll subtract our hypothesized mean from it. We're then going to divide it by our standard error using our concepts for Unit 3. That's going to be equal to the standard deviation sigma divided by the square root of our sample size n. Now, for this first possibility, we're going to assume that we know what the standard deviation is. Maybe we know it, we have very strong historical evidence for it, etc. Now, when doing this, you're going to then need to get a p-value from this test statistic, and you're going to get it in essentially the same way as the previous two units with your z-tables. Just like specified in the Chapter 9a lecture video, we can have one-tailed or two-tailed tests. If we have a one-tailed test, everything's in one tail. Two-tailed test, they're split evenly between the two tails. So, you might ask, what is this about? What is going on here? I get the probability of z being less than some value, but what does this mean? Well, the test statistic is this. So once you have that computation, that's what's going to be plugged in there. You might say, fine, why are we taking the absolute value of it, and then why are we making it negative? What's the point of that? Here's the reason why. By doing this, we take care of the complement law for you, so that way when performing your hypothesis test, you don't have to worry about that possible complexity ruining your hypothesis test conclusion. So for example, in the z-tables, for some z-score, it'll give you the probability of being below that value. So, let's suppose that your test statistic was down here. Well, then you'd look for, say, a -2. You'd be good to go, because it's everything to the left. But what if your alternative hypothesis was greater than some value, so you're instead looking for this? If you go into your z-tables, it's going to give you all of that. But you need what's above, so you'd have to use the complement law. But what if instead we took the negative of this value and went over here and got this area? Because the normal distribution is symmetric, it's going to have the same probability. So therefore, by taking the negative of the absolute value of the test statistic, we immediately take care of the complement law if it exists. You might say, what if it doesn't exist? Well, if it doesn't exist, suppose our z-score is a negative value. The negative of the absolute value returns the original thing back. So these two formulas will take care of the complement law for you. And as we recall for our two-tailed tests, that is indicated by the not equals to sign in the alternative hypothesis, which means we're going to have to double our probability from the table since it can be on both ends. It's okay if it's not perfect. Since we only have it for down here, we double it to get the one for up there. So with that, let's go ahead and go on to examples. Most of 9b and 10 are going to be working through practice examples because that's the best way to learn them. For all of these, if you're having difficulty seeing any of the text, feel free to zoom in with your device. I strongly recommend that if you have your z-tables with you, and for future problems, the t-tables as well, from the previous tests, to have them by your side to work with those. And as mentioned in previous videos, because this is a lecture video and not the in-person lecture itself, there won't be 4 minutes of dead time, for example, while students in class would be working it out. So go ahead, take a moment to work this one out, to pause the video, and then we will go over the answers. So for this one, to compute our test statistic z, we have a sample mean of 988.3, and we have our hypothesized mean of 940. We're going to divide this by the standard error, which we compute by taking our standard deviation of 230, and dividing it by the square root of the sample size 100. If you're having difficulty seeing this, this one is a 0. And this is going to come out to be a pretty nice and clean 2.1. So that is the value of the standardized test statistic. Now for our p-value, we're going to look for the negative of the absolute value. So we just look for negative 2.1 in the table. So here's our 2.1. There are no remaining decimals thereafter. So 0, 0. We find the intersection of these two, which comes out to be our p-value of 0.0179. We do not need to double this value because our alternative hypothesis is the greater than sign, so it's only on one tail. As for our conclusion, to make this text a bit larger, because our p-value of 0.0179 does not succeed, which means fall below, the value of alpha of 0.01 from earlier in the problem up here, we fail to reject the null hypothesis that the mean is 940, the true mean rather. And that is our first one. As you can see with a lot of it, it's more so bringing together everything you've learned thus far into one hypothesis test. So with that, let's move on to our next one. Once again, just like before, if you'd like to work this one out yourself, go ahead, pause the video, and then resume it when you are ready. So for this one, just like with before, we're going to take our sample mean of 944. We will subtract the hypothesized mean of 920. And we'll divide it by our standard error, which again we compute by taking the standard deviation that we know, 160, and dividing it by the square root of our sample size from above, which is 85. And this is going to be approximately equal to 1.383. Now, to get the p-value from the table, you might ask yourself, okay, we'll take the negative, so we'll look for our 1.3, and, well, I see an 8 up here, but where's the 8.3? What do I do from here? Well, here's the good news. First of all, let me show you what happens if we round it to the nearest decimal place and we go for the 1.38. If you do that, then you get your p-value of about 0.0838. You might say, oh, well, what happens if it's a little bit higher or lower than that? Because, Professor, shouldn't we technically be right about here? Say 0.083? What would that value then be right there? Well, that makes the p-value a little bit lower. So maybe it's 0.0831, for example. Well, here's the good news. Suppose instead the p-value was 0.0831. In that case, your answer would be off by a little less than 0.001. WebWork will have a rounding tolerance for every single p-value of 0.001, meaning if you get a z-score that goes out to the third decimal place or further, you can simply round it to the second decimal place, as we did here, in order to get the closest p-value. And then WebWork will take that. Furthermore, on the test itself, you're not going to see 0.083 as an answer instead of rounded to the third decimal place, 0.084. You're never going to have two test answers for the Unit 4 test within plus or minus 0.001 of each other. So here with all these z-scores and your p-values, you can very safely simply round the z-score to the second decimal place and be good to go. In any event, to continue on with our conclusion, it's going to be the same as before, but with different numbers. So to copy and paste it and bring it down, this time around, instead of having a p-value of 0.0179, we're instead going to have a p-value of 0.0838. And once again, we're going to compare that to our value of alpha. This time around, as you can see here, it's 0.05, so it's only one number we have to change there. And finally, we are failing to reject it, that this time around it's 920. So it would be a 2 there. I apologize to anybody who was traumatized by the 5 and the 2 recently inserted being of a slightly different line than the other numbers. You might say, Professor, that was lazy. Why not type the full thing out? Well, as you're going to realize when doing these hypothesis tests, the wording of your conclusions is going to largely be the same every single time. You're just going to have slightly different hypotheses and numbers to put in each time. Often in the real world, you will test various hypotheses to see which ones are the most plausible or which ones are ones that can be rejected. And so it's totally normal to have hypothesis tests with very, very similarly worded conclusions. With that said, let's go and move on to the final example for our one sample hypothesis tests. Just like before, go ahead and take a moment to work it out if you'd like to, and pause the video if so, and then we will go over the answers. For this one, once again, for our z-score, we have our sample mean of 1135. We will subtract the hypothesized mean of 1090. And we'll divide it by the standard error, which we compute by taking the 250 and dividing it by the square root of our sample size of 85. And this is going to be equal to about 1.66. So now to get the p-value in the table, once again, take the lower value, negative 1.6. Then there's our second decimal, the 0.06. We find the intersection of the two and get 0.0485 as our p-value. Notice that when compared to the problem a bit higher up, when it had the third decimal place, we don't have to worry about that this time because it'll just round off to the second decimal place. So we have our p-value of 0.0485. And once again, because our alternative hypothesis has the greater than sign, it's a one-tailed test, so there's nothing to double. But now things are going to be a little bit different with regards to our conclusion. So once again, we'll take our format up here and bring it down for just a moment so you can see how the wording changes. This time around, our alpha being 0.05 is larger than our p-value. So now we're going to get a rejection. And so for this one, for our wording, because our p-value of 0.0485, and if you want to, you can put value instead of just val, both are fine. This time, because it does succeed or falls below the value of alpha of 0.05, we reject the null hypothesis that the population mean is, in this case, 1090. And so again, as you can see, notice how in that first phrase, one word, this singular one word just flipped the whole answer. You're going to see this a lot with Unit 4, and particularly for the middle portion of the test. As you can see, that one not changes the whole answer, and not only that, causes us to change the wording in the second half of the sentence. So in this case, instead of having failed to, it's just removed. So 3 words, technically speaking, would change compared to a non-rejection. So when you're going through the answer choices on the Unit 4 test, and of course the ones with the web work and the practice test, pay very, very close attention to the wording, because all it takes is a couple of words to flip the entire answer. So I'll go ahead and get that out of the way so that you have the correct one. Those complete our hypothesis tests for one sample tests. So let's go ahead and continue on to what happens when we don't know the standard deviation. When we do not know the standard deviation, things get a little bit more involved. So here's what's going to happen. When we do not know the population standard deviation, we're going to have to use the standard deviation from our sample S. Otherwise, as you can see, the test statistic is computed in essentially the same way. We take our sample mean x bar, we subtract the hypothesized mean from it, and then we divide by our approximated standard error given by the sample standard deviation S divided by the square root of our sample size. Now, getting p-values for t-scores is considerably more annoying and tedious than it is for the z-scores. And so here it's easier to use the critical value approach. So instead of getting a p-value, we're instead going to get the critical value. And as discussed before, our critical value is the value at which, say 5%, if our value of alpha was 5% for a one-tailed test, of the data values lie below. So if this total area was 0.05, then this line would be the critical value, or crit. So if the magnitude of our test statistic exceeded that, then we'd have a rejection. So if the critical value was, say, negative 1.5, and our test statistic was negative 1.8, we reject the null hypothesis because that means our p-value should be below the value of alpha. So with regards to how to get these values, you get them from reading the t-tables exactly like with Unit 3. The only extra step you're going to have compared to Unit 3 will be taking your alpha and figuring out whether or not you have to divide it by 2. Because in the previous unit, we already assumed we were dividing by 2 since a confidence interval was two-tailed. Whereas here, if it's only one-tailed, the whole area is going to be in one part. Something important you will also need to note is whether or not your alternative hypothesis, or you call it alt, has the less than symbol or the greater than symbol. Well, those signs might confuse it a bit. Pay very close attention. If you have the less than symbol, then a rejection would occur on the lower end. So the less than would imply a rejection might occur down here. What that means is your critical value is going to have the negative sign. On the other hand, if your rejection would occur on the upper end, then you'll take the positive value. And finally, if you could have a rejection on either side, then you're going to want to have both values. And notice in the formula that what changes is whether or not we divide by 2. You can clearly see the dividing by 2 part coming from the reverse of multiplying by 2 for the p-values. Because doubling the p-value will be the same thing as comparing the p-value to alpha over 2. Otherwise, all the other computations would be the previous units, particularly Unit 3, combined together for a hypothesis test. So that, just like before, we'll go over some examples so you can get some good practice with it. So go ahead and take a moment, if you'd like to work on this one, and then we will go over the answers. So for this one, our degrees of freedom, we have a sample size of 5, so it'll just be 5 minus 1, which is equal to 4. If only the class was as easy as that, then everyone would have an A. Unfortunately, I believe it was a song that said, "Life's so hard, it gets so heavy, math is hard, welcome to life." I may have appended my own version of the lyrics at the end of that one. So here, let's start with the critical t value. how do we get that critical t value? Here's what we're going to need to do. So we have a value of alpha of 0.05. And the alternative hypothesis is that the mean is greater than 7. So because we have the greater than sign, our rejection, if it occurred, would be on the upper tail, the positive side. So this means our critical t value will be positive. Secondly, because it's a one-tailed test, as exemplified by the fact that we're only on this tail, we are not going to be dividing anything by 2 here, meaning this value of alpha of 0.05 will have all of our area in the upper tail. So we're going to look for 0.05 in this third column, just like with Unit 3, but with no dividing by 2. Then our degrees of freedom are 4. So now we look at the intersection, and we can see that our critical value has a magnitude of 2.132. And because, once again, we are using the greater than symbol, it will be positive 2.132. And for the test statistic, computed essentially the same way as with the previous tests, we're going to take our hypothesized mean of 7, and we're going to subtract it from the sample mean of 8.5. And then we're going to divide this by our approximation of the standard error, which is the standard deviation of the sample of 1.59, divided by the very poor and depressing sample size of 5. And this is going to give our resulting test statistic, despite the solid deviation, of about 2.109. And so in this case, we are not going to be able to reject our null hypothesis. Now you might say, well, there's no p-value, so how do you want me to word this? What should I be doing here? Well, in this case, you're instead going to compare it directly to the critical value. And the good news is you don't have to worry about the signs in your conclusion, because you can simply compare the magnitudes. Whether it's positive or negative, if the magnitude is not larger than the magnitude of the test statistic, then you weren't going to be rejecting to begin with. And so here, we fail to reject the null hypothesis because 2.109 does not exceed 2.132. Or to keep it in the format before, because our test statistics, I'll just put test stat, of 2.109 does not exceed the critical value, so I'll just put crit of 2.132. We fail to reject the null hypothesis that the mean is 7 of the population mean. Again, notice here, despite the fact that we had a solid deviation, the sample size was just too terrible. Just to really drive that point home, if we even had one more data point in our sample that gave us the same result of 8.5 for our sample mean and 1.59 for the standard deviation, and I'll go ahead and make that 5 look a little bit clearer in case it looks like a 6. If it was even one higher, then it would have been at 2.015 for the critical value instead, and then we would have had a rejection. So, lesson when you're on the job out in the real world, always ensure that you get a good sample size. Sometimes, when the conventional wisdom is just that awful, you don't need an incredibly amazing sample size in order to reject it. Sometimes you do. But in any event, you're not going to get a rejection with sample sizes this bad unless the assumption is just that terrible. So, in any event, let's go ahead and continue on to the next one. Just like with before, take a moment to work it out if you'd like to by pausing the video, and then we will go over the answers. So, just like before, we're going to go ahead and compute our degrees of freedom. This time our sample size is a considerably better, but nonetheless still disappointing, 8. We'll subtract that from 1, an incredibly difficult computation that only the most galaxy-brained of among us could compute, to get a value of 7 degrees of freedom. So once again, because we have the greater than symbol in our alternative hypothesis, it's going to be a one-tailed test, and we're on the upper side, so it's going to be a positive critical value. Additionally, our value of alpha is 0.05, so that 0.5 is going to be everything in that upper tail. So we're going to look for the 7, and this time we get a critical value of 1.895 instead of the higher 2.132. So that is 1.895. And now our test statistic, once again, computed same as before. We have the sample mean of 9.9. We subtract the hypothesized mean of 8.3, and we divide it by our standard error, which is computed from the sample standard deviation of 1.97, divided by the square root of our sample size of 8. And this is going to give us a test statistic of about 2.297. This time around, we're going to be able to reject the null hypothesis because even though our sample size is still bad, it's at least better than whatever on Earth 5 was. So this time around, because our test statistic of 2.297 exceeded the critical value, you could put exceeds, same idea, both are fine, of the 1.895, we reject the null hypothesis that the population mean is 8.3. You have a bit of room to work with for wording for some of these. You could also add, we accept that it's greater than 8.3, but as you can see, the crux of it remains the same. So let's go ahead and move on to one final example for the t distribution examples. So once again, just like before, go ahead and, if you'd like to, take a moment to pause and work on it, and then we will go over the answers. So for this one, our degrees of freedom, 7 minus 1, is going to be equal to 6. And so in our table on the right, we have our degrees of freedom of 6. Once again, our value of alpha is 0.05. Because it is a one-tailed test, as exemplified by the greater than sign, that entire 0.05 is going to be in the upper tail. At this point, I might say, Professor, why are we only going over examples of alpha being 0.05? What is going on here? Well, again, in the real world, far and away, 95% confidence, which corresponds to alpha being 0.05, is the most common confidence level you're going to run across. So it stands to reason you're going to have at least a plurality of your examples involve 0.05. So with that, as you can see, the intersection of these two is 1.943. So we get our critical value, which will be positive, of 1.943. Now for our test statistic, we don't have that much of a deviation. It's 8.3 versus 8, so we have 8.3 minus 8, and we divide this by the approximated standard error by taking our sample standard deviation of 1.33 and dividing it by the sample size of 7 being square rooted. And this is going to give us a test statistic of about 0.597. And this time around, it comes nowhere close to being a rejection. At least the first one came somewhat close. So for here, because our test statistic of 0.597 did not exceed the critical value of, and again, when you want to include the ofs, is up to you, same point is made, of 1.943, we fail to reject the null hypothesis that the population mean is 8. As you can see here, when compared to the previous possibility of knowing the standard deviation, the main difference comes in, instead of getting a p-value, we get the critical value because that's easier and more intuitive. The rest of it stays essentially the same. So with that, we are going to move on to our final possibility for our one sample tests, and that's when we have proportions. Now for a proportion, the standard deviation is based on the proportion itself. So to zoom in on that for you, in case you're having difficulties seeing it. Because the standard deviation is based on the proportion itself, that standard deviation comes from the hypothesized proportion P naught. Otherwise, again, the rest of it remains the same. The good news here is the only difference between our hypothesis test for one sample proportions and one sample means, where we knew the standard deviation, is just the denominator for all intents and purposes. I mean, technically these letters are different, but it's the same idea of taking the difference between what you got and what the hypothesis is. And otherwise, the rest of it's the same. So the computation of the test statistic is a little bit more involved than the one sample z-test, but everything else is going to be the same. Because again, it's still going to involve the normal distribution. And I'll note for all of these, if you need any extra time to write any of them down or what have you, always welcome to take a quick pause with the video to ensure you get the time to write that down. In the in-person lectures, we'd of course take a minute or two to ensure that everyone can write it down before discussing it, but since we're going over a video, we have the advantage of the pause button. Imagine if you had a pause button in real life. Wouldn't that be an interesting thought experiment? Which people could be trusted with it? Who knows? Who cares? This is a math class. Let's get on to boring you to death with numbers. Now with these, you're going to get a lot more context questions to help you with practice with applications. Now, an important thing to note, and this has been stated before in previous lectures, but it's always worth stating it again as a disclaimer. When we have proportions, there are going to be poll and survey results. Sometimes they involve things that are, say, related to business. Sometimes they involve customer satisfaction, the percentage of people that agree with something or disagree, support, oppose, etc. In this class, as I've mentioned before, we will use examples from all across the spectrum, but as you've very clearly seen, we are not commenting on the underlying issues themselves. We're just doing the math. If they want the discussion, I'm pretty sure the poli-sci department can certainly discuss that. But as many of you will very quickly see, and probably have already seen many times before in this class, it is very difficult to talk about polls without talking about, well, polls. So for this one, go ahead and take a moment to work it out, pause the video, and then we will go over the answers. So for this one, we want to state our hypotheses. So we have our null and our alternative. So for our null hypothesis, we're testing to see if greater than 2/3 of Americans support gay marriage in this given poll. This was actually a Gallup poll back from, I believe, 2019, if I recall correctly. I wouldn't be surprised if the numbers were higher since then. So for here, we'll just take our proportion P, and technically speaking, you can put less than or equal to 2/3, although as you can see from the poll result, we have no reason to suspect it's going to be less than 2/3, so keep things simple. It'll be the equal sign. You might say, Professor, what happens if I'm taking a test and you show me both those options? The good news is that's impossible, not going to happen. You're not going to have one null hypothesis with the equal sign and the other with less than or equal to. It's not going to happen, not going to be a thing. And as you've probably seen many times already, it is pretty standard practice to just not even consider the possibility that is very far off both from the null and what your evidence suggests. If our conventional wisdom was that it was about 2/3 support and our poll comes up 70%, you'd have to be a bit of a crackhead to think the correct answer is 60%. So for here, our alternative is that the P is going to be greater than 2/3. Next up, we need to state the value of alpha, which is going to be equal to 1 minus our confidence level of 95%, which is 0.95. So that is equal to 0.05. Now, to get our p-value approach and use our z-tables off to the right, we got to get our test statistic, which is going to be equal to the poll result of 70%, so 0.7, minus the hypothesized percentage of 2/3, so I'll just put in 2/3. And then we will divide this by the standard deviation, which was that numerator part, of 2/3 times 1 minus 2/3. And then this will be divided by the square root of our sample size, which is a very solid 1,000. And this is going to give you a test statistic of about 2.236. Now, some of you might look at that and think, wait a minute, I got 2.214. Where'd this come from? Well, if instead of using 2/3, you put in 0.667, then you would have gotten 2.214. But guess what? In that case, they're only off by 0.002. So by definition, you're not going to have an answer of 2.233, for example, or 2.229. That's not going to happen. Again, as I mentioned on the test, you're not going to have two answers that are within 0.001, or honestly 0.002 of each other as well. But again, when doing these computations, if you have a fraction or you have a repeating decimal, I strongly recommend you use the whole decimal and don't do any rounding until the very, very end to ensure that you're good to go. So for this one, we're going to take that 2.236 and we're going to go into our z-tables. So here is the 2.2. So now, with regards to the 3.6, it's going to be somewhere in between these two. And so that means you're going to be somewhere in between these two values. But guess what? Suppose you instead use the suppose you use the 0.03. You get 0.0129. Rounded to the third decimal place, that's 0.013. If you instead took the 0.04, you get 0.0125. Rounded to the third decimal place, that's 0.013. In both cases, third decimal place round off gives you the same answer. If, again, you had used the rounded 2/3 as 0.667, then you would have gotten a p-value of 0.0136, a bit further to the left, which rounded to the third decimal place would have been 0.014. Again, though, that's within 0.001 of the correct answer, so you'd get it marked as correct. Again, as you can see here with the p-values, unless your z-score is wildly off, you should be okay on rounding. In any event here, because the 6 is roughly halfway in between these two, your p-value is also going to be roughly halfway in between those two, so it's going to be about 0.1, I'm going to put the extra 0 in front, 0.0127. And with that, we then arrive at our conclusion. So as I scroll a bit far down, don't need that space. We can put it over here. So here, because our p-value of 0.0127 subsedes our alpha of 0.05, we reject the null hypothesis that we'll say 2/3 of Americans support gay marriage. And here you could say it's therefore greater than 2/3. Again, for this p-value, if you're wondering where that p-value came from, it's about the halfway point between these two. If you put 0.0129, that'll be marked as correct. If you put 0.0125, that'll be marked as correct as well. In fact, again, if you rounded this off to 0.667 and instead ended up with 0.0136, that'll be marked as correct as well because, again, rounded to the third decimal place is within plus or minus 0.001, and you reach the correct conclusion for the right reasoning. As side note here, notice that with our conclusion with the math, we stop there. If you, again, want to add the extra sentence of, and accept the alternative hypothesis that greater than 2/3 support gay marriage, you're good to go. Notice that we do not say what exactly that number is, because it could be 71% and we had a small poll error. Or maybe it's actually 73% and it's a little bit larger of a poll error. In any event, we do not try to pin down exactly what that value is, and we certainly don't make any comments on how any policy or anything whatnot can be done with that. It's a math class. We'll stick to the math. So with that, let's go ahead and move on to our final example for this lecture. Another applied example in a similar vein. Go ahead and take a moment. This was a poll that actually occurred. And come to a conclusion after conducting a hypothesis test. All right. For this one, once again, we have our two hypotheses. For this one, we're trying to test if they're about equal in terms of volt share. So it's a battleground. If they're equal, then that means they're both around 50-50. If it's 49-49, they go to a runoff, still 50-50. So here, the null hypothesis is that it's 50-50. Therefore, the alternative is not equal to 50-50. This is the first time today you have the not equal to sign. Usually, you're going to have a one-tailed test when dealing with one sample test. But every now and then, you'll have a two-tailed test. So, if you didn't notice that it was a two-tailed test, you're welcome to pause again and double-check your work, particularly for the p-value. But if you did, then feel free to sit back in your chair and have a big grin on your face. In any event, let's keep going. Our value of alpha. This time around, we're looking at a high confidence level of 99%. Because in this case, one sentence seed can change everything. So we take 1, we subtract our confidence level of 99%, and that gives the actual value of alpha, instead of being the usual 0.05, is now 0.01. So now let's compute our test statistic z. This is going to be equal to the poll result, which was 51%, ended up being essentially the actual result, subtracted from the hypothesized proportion of 0.5, and then divided by our standard error, which we get by taking the 0.5, subtracting that from 1, which gives the same thing back, and then divided by the square root of our sample size of 499. A common mistake that many people will make when computing these tests is they'll mess up and they'll take the 0.51 and stick that in for these two. If you do that, then you're going to get slightly different results, and although you may accidentally stumble upon the right conclusion, that'd be for the wrong reasons. In any event here, we're going to get a very disappointing test statistic of just 0.447. We take that value, go into the z tables. We'll look for the 0.4, which is right here. And the 47 is pretty close to what in this case would be the 0.5, so we're just going to take that and run with it. And this time, we have much larger arrows, because our test statistic is very pitiful, and we get 0.3264. That's going to show up as an answer choice, and it will only receive partial credit. And the reason why is because we have a two-tailed test. Two-tailed means we have to double that value, meaning our p-value will be equal to 0.3264 times 2, which will be equal to the correct p-value of 0.6528. In either case, you're obviously not going to be rejecting a null hypothesis, so if you did all of this but then forgot to multiply by 2, you'd be looking at around 80 to 90% of the credit depending on how the questions are weighted. So forgetting to multiply by 2 is not going to cause the whole thing to be marked as wrong. As has been the case with every test in this class, you will be awarded partial credit as has been earned. This is not going to be one of those classes, as you have seen, where mixing up one tiny step causes you to be thrown off the Grand Canyon or something like that. In any event, to get our conclusion, because our p-value of 0.6528 does not subsede the alpha of 0.01, we fail to reject the null hypothesis that the population proportion is 0.5, or in this case, to convert to English and still be correct, that Georgia's Senate race was a battleground. Now, if you went up to one of the media pundits and you said this, they'd have looked you all in the eye and either say, no shit, or just laugh you out of the room. But sometimes that's how the world works. You get a result that is exactly expected. And sometimes you'll get a result that's not expected. Such is life. In any event, that concludes our hypothesis testing for the one sample tests. In the next and final lecture, assuming you've already gone over chapter 13, we will go over some of the two sample tests, particularly the two variants that are far and away the most common in the real world. So with that, have a great rest of your day or night or evening or whatever it is, and I would say see you again, but I'm more like speak to you again in the chapter 10 lecture video.